Across industries today, from warehouse automation to agriculture and manufacturing, autonomous vehicles are revolutionizing how efficient work gets done. These systems are designed to move with precision, respond to their environment, and operate with minimal human intervention. In this video, we will explore the foundations of these systems using the RedBot, a compact AI-powered robot that simulates the behaviors of real-world autonomous platforms. With its onboard Jetson nanocomputer, camera, and drive motors, the RedBot gives us a hands-on introduction into robot autonomy. Throughout the video, we will discuss how the RedBot learns to perceive, decide, and act. With that, we started with the basics, getting our RedBot to moving and under control. That all began in Lab 1.
In Lab 1, we focused on the foundation of robotics, motion control. We began by learning how to communicate with the RedBot using Python through Jupyter Lab, a browser-based programming environment. This allowed us to send motor commands and test how the robot responded. Next, we performed autometric calibration. Since the RedBot doesn't have wheel encoders, we estimated its speed by measuring distance traveled over time. We also adjusted motor bias values to ensure it moved in a straight line, a critical step for accurate autonomous travel. Using that data, we applied forward and inverse kinematics to control the robot's position. In our final task, we programmed a sequence of maneuvers, including a 90-degree turn at an intersection by breaking the path into translational and rotational segments, and calculating how long each should take. Once we had motion control and kinematics down, the next step was perception, teaching the robot how to see and react to its environment. That's where Lab 2 came in.
In Lab 2, we moved from basic motion to reactive control, teaching the RedBot to follow a line using its camera. We implemented a vision-based feedback loop where image processing determined the robot's position relative to the yellow path on the track. By calculating the heading angle between the robot and the path, we applied a PID controller to generate motor commands. The proportional term handled the immediate error correction, while the derivative term added dampening to reduce overshoot, so the robot can effectively stay on the path. Later in the lab, we shifted to focus to machine learning, where we trained a deep learning model to classify road signs, stop speed, and to react to there being no sign at all. Using machine learning, we were able to collect and label images into specific groups and then train the model with real-time feedback until it achieved an accuracy of well over 85%. With the visual tracking and sign recognition under our belt, it was time to give our robot some awareness to the bigger picture at hand. Where it is and where it's going. That was the focus of Lab 3.
In Lab 3, we focused on one of the most complex tasks in autonomy, localization and navigation. First, we connected the RedBot to a ceiling-mounted camera bot through SSH networking and had it capture overhead images of the robot's position. We then calibrated the camera to remove lens distortion and used Apple tags, which are visual markers, to determine the RedBot's exact X and Y coordinates and orientation. This real-time localization was essential for mapping. Using this information, we performed path planning in MATLAB with a probabilistic roadmap. The goal was to calculate the shortest path through a grid of intersections to a final target location. Our algorithm translated the robot's pose and map data into clear driving instructions. Go straight, turn left, or turn right. The integration of networking, camera calibration, computer vision, and path planning brought us to the closest to a real autonomous navigation system and laid the groundwork for our final demo. After building individual functions, we needed a way to connect them into one cohesive program. We designed a flowchart to plan the robot's logic from start to finish.
To integrate all concepts we learned, we developed a logical flowchart that outlines how the RedBot would navigate autonomously from a starting point to its destination. Our program begins with 4 essential inputs: initializing the RedBot, loading the destination coordinates, loading the map image, and converting pixel data to real-world scale. Next, the robot performs camera calibrations to correct lens distortion, then use April detection to determine its starting location. With this location and the goal defined, we apply path planning, which outputs a list of waypoints or directional commands to follow. The robot then enters the path following stage using visual line tracking and PD control to navigate the road. At intervals, it performs April tag relocalization to correct for drift or errors in positioning. While following the path, the red bot also performs sign recognition using deep learning. If a sign is detected, the robot takes specific actions based on its type. If it detects a stop sign, the robot pauses for 3 seconds. If it detects a speed limit sign, it reduces the PD controller gain to slow down appropriately. If no sign is detected, the program checks if the robot is at an intersection. If so, it relocalizes using April tags again, and if necessary, replans its path based on the updated position. Finally, the robot continues this loop until it determines that it has reached the destination, specifically when the difference between its current coordinates and the destination is approximately 0. This flowchart allowed us to clearly define each subsystem's role and how they interact. From sensing and planning to reacting in real time, it served as our roadmap for building and debugging the full autonomous behavior.
Our final demonstration showcased the Jetpot autonomously navigating from point A to point B. It began by driving forward using calibrated kinematics, adjusted its trajectory by following a yellow path using the PD controller, and finally detected a traffic stop sign to make a stop. This project demonstrated our ability to combine multiple engineering disciplines: control systems, computer vision, machine learning, and algorithmic thinking, all in one robot.
This project was much more than just programming a robot. It was a deep dive into the systems that make autonomy possible: motion control, computer vision, machine learning, and systems integration. By working hands-on with the Redbot, we did not just learn theories, we applied them. From calculating the motor speeds using kinematics, to developing a PD controller for precise path tracking, to training a neural network to recognize road signs. Every lab built upon the last. One of the most rewarding parts was seeing how all these components came together. Our final demonstration wasn't just a robot driving around, it was a culmination of everything that we had learned functioning as one cohesive system. This experience also taught us the importance of teamwork, problem solving, and iteration. Not everything will work the first time, but that is where we grew the most. Troubleshooting bugs, calibrating the sensors, and refining our logic until the robot did exactly what we envisioned. As the world rapidly advanced towards autonomous technologies and logistics, manufacturing, agriculture, and much more, projects like this gives us the skills and the mindset to lead those innovations.
How do you feel about the bot's performance?
I'm really proud of him, he did his thing, number 12, man. He number 12, but he really number 1. I'm really proud of him.